Okay, a couple things before we get started. One, if you ever go to the course website, make sure you're refreshing it every once in a while, because sometimes your browsers will cache the website and not realize it's been updated, but it has. So just make sure every once in a while you're hitting refresh to make sure all the content is actually being shown to you. Another thing, on assignment 3, there's one of the problems, it's like 5 or 6. One of the questions is like the print game board or something. That is going to be a tricky problem. I'm warning you now. That is going to be one of the trickier ones of the assignment. It's kind of by design because it's, I don't want to say easy, but it's easier to debug because when you hit run, it's very visual and you can see the changes in how it affected the output. But just be warned that that one is supposed to be a little bit on the tricky side. And another thing. So one, I was really happy with people actually came to office hours today. It was very exciting. But one of the things that came up at office hours was, so every other year, I've been teaching this stuff for 6+ years. And during those years, there wasn't a global pandemic. So it was a lot easier for students to just like organically meet and kind of like form study groups and work together and whatnot. You know, not cheating or anything, but like, you know, learning, peer teaching, figuring things out. Oh, I have a problem, can you help me? That type of stuff. It happens every other year. But this year, it's going to be a little different. It's going to be weird because of social distancing. You won't get to know people as well. There's all these things. So one, it's critical because of this that you're making use of the support that's made available to you already. That's like the tutorials, the TA, the undergrad TA office hours, the graduate student TA office hours, my office hours. Make use of them. But it was suggested that maybe you can kind of find and coordinate online study groups. So, one, it was Donica, who's in here somewhere, right? Where are you? There you are. She had suggested, so you created something on Facebook, right? So there's like a group on Facebook people can join, but that's also her like email address right there. She's told me that you can feel free to reach out to her saying, hey, I'm interested in blah, blah, blah. Make use of this. This is a great opportunity to do a lot of peer learning, peer teaching, and just understand this stuff better. So make use of this. And she's also a 4th year student, which maybe that doesn't mean much to you, but you know, 4th year students kind of tend to have figured out university a little bit. So, you know, take advantage of this. She'll probably have a lot of really good information. There's probably going to be students from every year joining the study group too, so it's a great chance to meet students who are a little more senior than you. Every other year it happens organically, and you'll notice on Collaborate, on Blackboard Collaborate, one of the links at the very bottom is like the general group discussion meeting place. That might be a great place to like have scheduled, like, hey, you know, let's, schedule a time between this time and that time. That link on Collaborate might be a great place for you to meet and chat and whatnot. I mean, use whatever resource you want, but that's there for you. It was kind of designed for like, oh, you know, I'm working on this, anyone else joins, whatever. So this is a really good opportunity to have that like student support network that would happen organically every other year, but this year it's a little bit more difficult because, you know, global pandemic and social distancing and everything. Any questions about that? Anyways, once again, that's Donica up at the back. She's the one that's kind of decided to self-organize. Awesome, I love that stuff. Cool. All right. Any questions before we get going? In general? Who here started assignment 3? Wow, awesome, good. That's wonderful news. Who here is thinking, yeah, it's really hard? Yeah, it's a tough one. This tends to be the one that gets to people. A couple of people that came to the office hours, just as I had expected, this is not being critical in any way. It's so typical that the issue ends up coming up to be the whole, wait, is that a list or is that a pointer to a list? Do I have multiple pointers to the same list or do I have separate lists? That's always the difficulty, or one of the difficulties in this assignment. So if that's you, you're remarkably typical in a good way. Okay, so I think last time I blitzed through NumPy, mostly because it's very, very, very similar to lists, and if you ever want to use NumPy, well, you know the basics, and then you can go learn anything else you need to know to use them for yourself. So next, we're going to learn about tuples, dictionaries, and sets. So we've seen tuples already. The first assignment had a tuple. Raise your hand if you remember the tuples in assignment 1. 1, 2 people. So they kind of snuck in there. The tuples, pardon me, were the coordinates of the Starbucks locations. So when you read in that file of all the Starbucks locations, the computer in that function, that load assignment 1 data, stored the coordinates, the latitude, longitude pairs in a tuple. But really at the end of the day, you probably might remember like, well, to get the information out of the tuple, you just indexed it like a list. And yeah, you're absolutely right. Tuples are going to be very similar to lists. If I do something like this, it looks similar to creating a list, but of course it doesn't have the square brackets, it has parentheses. If I print out the tuple, we see it with the parentheses. So let's go test this out. Great, cool. So, if it's so similar to a list, well, what's the difference? So here's what I want you to do. Take 2-3 minutes, create a tuple, and see what you can do with it. See if you can find out what's different about tuples from lists. Raise your hand if you found something different. No, nothing yet, eh? All right, keep going. I'll give you a minute. Well, I just found one. Saying tuple object does not support item assignment. I mean, with lists, I could definitely do this, right? I mean, just like a list up here, I printed out tup at 0, which gave me 5. But I tried to put in an x into tup at 0, and it's saying you can't do that. It was kind of like a string. Remember how strings? You can access individual letters in the string, but you couldn't change them like you could change individual elements in a list. Yeah?
You can't append stuff to a tuple?
You can append. Interesting. So, actually, first, before I go into looking at that, I want to see if I can have different types in the same tuple. So it looks like I got different types like lists, so that's cool. Because remember how numpy arrays, they all had to be the same type. But I guess with tuples, you can mix and match again. Now, you were saying tup dot append? You were doing something like that? Let's append 7. Oh. I don't know, didn't seem to work too well for me. So it did or did not work for you?
It did, like you can append stuff to a list, but you can't.
Oh, but you can't with tuples. You're right, we can't. Yeah.
You can kind of do it by adding two tuples together.
Let's have a look. So kind of like the concatenation, eh?
Yeah.
So if I've got tup, I don't know, let's say I have put. Tup plus put. Let's see. Yeah, it looks like that worked, but I suppose, I mean, I'm going to want to check tup. And it looks like tup is left unchanged. So it looks like when you concatenate them, it creates a new tuple that's the concatenation of the two. Which also, that kind of worked that way with lists. But it's good to know that, this is how it works. Okay, cool. Yeah?
I think cool. I just like said like tup. Well, in your case it would be tup plus put. Tup equals tup plus put. So like you didn't actually.
Yeah, so by doing that, now tuple changed, but that's because we took tup, we took put, concatenated them, and took that new thing and assigned it to tup. So it looks like the key main difference here is that, I guess I can't, look, there's a way less built-in functions, eh? Remember with lists how there was like a whole bunch of things you can do? With numpy, there are a whole bunch of things you can do. With tuples, they're immutable, we can't change them, okay. So they're clearly less flexible than lists. Kind of like, numpy arrays had less flexibility than lists in some ways, but more power in other ways. It's the same idea with tuples. Tuples are simple. But with that simplicity, sometimes we get like speed or something. So it's always a trade-off. A cool thing about tuples, if you're using numpy arrays, is this. I'm gonna show you here. I'm just going to show you, you don't have to actually care. So I have something like this. This is a numpy array, not a list of lists. It's a numpy array of numpy arrays, two-dimensional. And I've got 0 through 24. 0, 1, 2, 3, 4, 5, 7, 9, and so on. Great. We also saw that we can index this as like 0, 1. And we should see 1. 0, let's do like 1, 2. 7. Okay, great. Cool. But we can also index numpy things like this. We don't actually need to do the 2 sets. NumPy lets us do it with like a comma, which is kind of cool. But we can also even actually pass it a tuple. Or like chord equals, I don't know, 1, 2. Ooh, neat. If you're like, okay, cool, why do I care? All right, fine, whatever. You don't have to. I'm just showing you like you can do that. It's pretty cool. You can pass a whole tuple object, and NumPy is smart enough to go index it accordingly, which is pretty neat, I think. Great. Yeah, okay, I just showed you that. Great. Okay. Any questions about tuples? If you never use a tuple for the rest of your life, fine, whatever, I don't care. I'm just showing you that it exists. The next thing though, oh yeah.
Could you get like a user input and then turn like 2 numbers in the input into a tuple?
So let me see what you mean. I think I know what you mean. Why are you asking that question? You're just curious. Okay. Huh. So what if I do like A equals input, B equals input, right? Oh, I'm probably going to want to make these ints, right? And then maybe I can do like chord equals AB. What numbers do you want me to put in?
1 and 2.
1, 2. Look good. So yeah, it looks like we could do that. Whoop, wrong way. Okay, so tuples, if you don't really use them for the rest of your life, fine. But dictionaries, on the other hand, you're going to love. Whether you realize it right now, you will inevitably one day love dictionaries. They're amazing. They're like computer scientists' favorite thing. So a dictionary is going to seem a lot like a list. Here's a way to create an empty dictionary. So I'm just going to take this. Great. It looks like I just created a list, or a tuple, but instead of square brackets, instead of parentheses, I use the squiggly brackets. Cool. Just another way of collecting and holding on to information. Great. I know about numpy arrays, I know about lists, I know about tuples, dictionaries. Now it's just a whole other way of storing information. You're not wrong, but you're wrong, because these are magical. Dictionaries, okay, if I do this, this looks a lot like, if I just change this to an empty list, it looks the same, right? So far, not much different. But I can add things kind of like this. There. So I added something. But we will see that, like, okay, what are we observing here? All right, we created an empty one, and then I added something to the dictionary, which is a little different than lists, right? Because with lists, if I wanted to add something, I'd probably append, right? Append is the way we've seen about adding things. Okay, great. But here, I'm saying, no. My dict at index, the string James, is equal to 50. It's a little weird, right? I mean, this is definitely different than lists or tuples or numpy arrays. I am explicitly saying my dict at James equals 50. But, like, with numpy arrays, with tuples, with lists, the indices were always integers, right? If you start at 0, then there's 1, then there's 2, and so on. Here I'm saying James. And then if I say, and I print it out, I see like, it's kind of got like James colon 50. Let's go back. What else do I say? I'm going to add these things too. There. Now it's James 50, Susie 95, Johnny 85. They seem to be like paired pieces of information. These are what we call like key value pairs. And they all have strings, which is weird, not indices. But I guess, okay, maybe we can just index these things with strings. Okay, great, cool. Maybe these represent grades or something. Maybe James got 50 in the class, Susie got 95, and Johnny got 85. Arbitrary values, yeah.
So with lists and numpy arrays, you have 2D lists or numpy arrays, and you also have 2D dictionaries.
Why don't you try it? Try it and tell me. Before you try it, what do you think the answer is?
Hopefully.
Hopefully? Hopefully. Okay, cool. Okay, so if we're assuming that these are like, grades, student grade pairs. So, yeah, we call these key values. Dictionary at a certain key will give you the value. In the same sense that, like, well, a list at index 0, let's say 0 is the key. It'll give you the value at 0. So here's what I want you to do. Take a couple minutes, 2, 3 minutes, and do this activity here. Make a dictionary like the above. Find out how to access values associated with a particular key. So before, I assigned values to the key, but I never got the value back. See if you can figure out how to do that. And yeah, do this activity. See if you can do all the things and bits there. Raise your hand if you figured out how to access an element. Really high, I want to see. So most people, let's figure that one out real quick. So I wonder, like if I assigned it that way, kind of like a list, but of course the list had to have the thing existing first. I don't know, let's see if I do this. Cool, great. Is this what you did? Yeah. Cool, yeah, there you go. And then the next question was, what happens if you try to access something with a key that's not in there? Well, it suddenly tells me, like, key error, J. That's Python's way of saying there is no key J. And if there's no key J, I can't tell you what value is associated with it because it's not there. It doesn't exist. Makes sense, I suppose. So dictionaries are generalizations of lists, kind of. But instead of indexing things with integers, 0, 1, 2, 3, and so on. And also keep in mind, like lists are ordered, right? You start at index 0, then index 1. There's an ordering there. But here, we're indexing things with the strings. And then there's the values associated with it. The values could be whatever we want. Did you answer the question about dictionaries of dictionaries? Could we do it?
Yes, you can. It's just a bit weird, though.
You can. It is weird, but did that surprise you? A little bit. Computer science is weird. It gives you a set of rules, and as long as you're operating within those rules, it lets you do your thing. And also here I'm saying like, oh, it lets us associate arbitrary strings with values, but technically we can do whatever we want. We could have dictionaries where we have integer value pairs. We could. We could have a whole bunch of other things. They don't have to be strings. They have to be what we call like hashable, but let's not worry about that right now. That's an issue for like second year computer science. There's also some functions available. You may have done this already, but if I go down and say dict dot, there's a whole bunch of things. Clear, copy, from keys, get items keys, pop items, set default, update. Great. What happens if I say keys? Oh, that tells me it's a function. I guess I have to call the function. Great. Oh, here are the keys. James, Susie, Johnny. Great. Cool. In fact, I'm wondering, can I do something like this? For k in, if that gives me back something that kind of looks like a list of keys, I wonder if I can iterate over those keys with the for loop. Let's have a look. K, or I guess at k. Looks pretty good. In fact, maybe I want to do like this. Print out k and then, yeah, well that's cool. So there's an easy way to iterate over the contents of a dictionary. Interesting. Or, I mean, big surprise. What do you think values is going to give us? 50, 95, 85. So instead of giving me the keys, give me the values. Here's a special catch, though, about dictionaries. This may be painfully obvious to you already, but maybe not. I'm going to say it anyways. The keys must be unique. They have to be unique. You cannot have two of the same keys in your dictionary. And this might be obvious if we kind of write it out like this. If I want to add James again and give him 51, well, it's not going to work because all it's going to go do is find the value associated with the key James that's already there and update it. We can't have duplicate keys. We can't. So the keys must be unique. Do you think the values have to be unique? I see a bunch of people going, and when you think about it, I mean, I suppose if they had to be unique, it would be arbitrary, because there doesn't seem to be a rule why it has to be unique. Keys make sense. We can't have duplicate keys because one key gives you the associated value. I can't have two unique keys, pardon me, one key give me two values. That's not a thing. But I can have multiple keys give me the same value. Great. So the keys must be unique, but the values doesn't matter. Any questions about dictionaries so far? So, quick poll. Who's thinking, oh, okay, cool, great, whatever. You know, a bunch of people. Yeah, like, okay, it's just a list, but you can index with strings. I can see how that's handy. Oh, it gets way better, though. Okay, so many programming languages, they'll have key value pairs. They might not call it a dictionary, but they will have effectively this, dictionaries. Key value pairs. You have a key, it gets you a value. It's a mapping. So let's do a little thought experiment. Let's say, okay, what's the question? We have a 2D list like this. So throw dictionaries out the window for a second. Forget that they exist. They don't matter right now. I've got a list of lists. I've got grades, which is, I suppose, a list of my students in my class. And then within them, I have a list. I've got multiple lists, actually. I've got 1, 2, 3, 4. 4 lists. And each one of those lists represents the student name and what grade they got. That's it. So grades at 0 gives me the list James, 98. If I say grades at 0, 0, it gives me James. If I say grades at 1, 1, it gives me 86. In this example, the inside lists are always going to be just pairs. It's a list of size 2. And that makes sense for this example. Let's say I gave you this list. Let's say it is 100 students long. Okay? There's 100 students in here. And I ask you, you've got grades. All you have is grades. And I ask you, what do I have there? What is Andrew's grade? Okay? Now, I know in this example up there I've got 1, 2, 3, 4 students in it, but pretend there's like 100 students. And I ask you the question, what is Andrew's grade? All right, well, how are you going to find that? I suppose I have to do a linear search, start at the beginning of grades, the list grades, and check the insides list, index 0, and say, are you Andrew? If I am, great. Return the inside list, index 1, that's the grade. But if it's not Andrew, what do? Go to the next one. If that's not Andrew, what do? Go to the next one. It's a linear search. Do a linear search, probe the inside list, index 0, because that's always where the student's name is. And if it's what I'm looking for, return inside list at index 1. That's the grade. Does this make sense? This is a linear search. We've been talking about it for a couple of weeks now. If there is 100 students in the class, worst case scenario, let's say there is no Andrew in the class. How many things do I have to look at before I know? If there's 100 students, how many things do I have to look at? All of them, 100. What if there's 200? How many things? All of them. If there's n, how many things? N. I got to look at all of them, no matter what. I start at the beginning. Are you Andrew? No. Are you Andrew? No. I got to put my finger on each one of those things until I find it or get to the end. Worst case scenario, it's not in there. I have to look at all the things. Linear search. Things that are like linear. Things that, well, let me put it this way. I'm going to ask one more set of questions. We already answered this one, and I want everyone to answer. If there are n things in the list grades, how many things do I have to look at? N. What if I had 2 times n things? How many things do I have to look at? I heard a lot of mumbles. 2n. If I double the size of n, if I double the size of the input, I double the amount of work I have to do. This is typical, and it's not that bad. We don't want to spend more time running an algorithm than we have to. And if you think, well, in order to find something, I got to search can't really think of doing anything better than that, right? Like, can you think of a faster way to find if Andrew's in that list? Probably not. You got to start at the beginning and go, are you Andrew? Are you Andrew? Are you Andrew? And if there's N things, you got to look at them all until you find Andrew. So it's linear. Not too bad. But here's the thing. If it was a dictionary, all I would have to do is, like, assuming this is a dictionary of key value pairs where the keys are the students, their names, all I would have to do is say, oh, grades at Andrew. What grade did you get? There's no loop. I just said, hey, tell me grades at Andrew. I didn't have to do a linear search. Just tell me grades at Andrew. I know. Now hold on, but before I move on, I want to make sure I'm really emphasizing this. If I have this, where am I going? I'm all over the place. So I'm going to have to write code that's like, okay, for I in range len of grades. Okay, if grades at I at 0, because the 0th one is always the name, is equal to Andrew. Whoop. Return grades at I1. I guess not return, just print, because this isn't a function. Otherwise, just carry on. There's nothing there because there's no Andrew. But maybe I'm looking for Greg. Okay, great. We found Greg. It was 59. Let's make sure this makes sense. Grade is like a list of lists. Really, grades is like a pointer to a list which contains pointers to different lists. But for simplicity, it's a list of lists. Grades at 0 is James 98. Grades at 1 is Bob 86. Grades at 2 is Janice 86, and so on. So grades at I will be the current student. Grades at I at 0 will always be that student's name if we're following the proper convention that I've laid out here. And grades at I at 1 will be the associated grade. So this is an example of that linear search. I have to go through it until I find what I'm looking for. However, if I want it's as easy as that. So hopefully you see the difference. I didn't need to write the code for a linear search. But, and I'm going to poll the class. Raise your hand if you're thinking, well, hold on. I remember we saw that in operator before, right? I remember we could say, oh, is something in a list? And although that was nice one line of code, we knew in the back end it was still doing that linear search for us. It was just a shorthand for a linear search. We remember that, right? So raise your hand if you're thinking about that and saying, but is that just the same thing? You know, oh great, you made a shorthand for a linear search. Well, we didn't. We didn't. It doesn't have to do a linear search. Asterisk. This right here, it just looks it up. So, with the list of lists, if I wanted to find something, I have to do a linear search. And if there's n things, I have to look at n things. If there's 2 times n things, I have to look at 2 times n things. If I double the size of the input, I double the size of the work. The amount of work grows proportionally, linearly with the size of the input. Okay. But let's say there are, what do I have? 4 students. How many things did I have to look at here to find it? 1. Let's say I had 100 students. How many things would I look at here? Who knows? It's not really a trick question. It would still be 1. If the dictionary is size 100, I just go look up Andrew. It's still 1. Let me ask you this. If the size of the list was n, how much work do you think this would be? Who's bold enough to take a wild guess? It's not a trick question. Who said 1? Raise your hand if you're saying 1. Yeah, it's 1. If there are n things in that dictionary, it's still, just go look up the thing you're looking for. There it is, found it. No linear search involved. What if the size was 2 times n? How much work is there? 1. What if it was 10 times n? How much work is there? 1. This is interesting. Notice the difference. When we were having to go through the list, the amount of work we had to do, if we doubled the size of the input, the amount of work we had to do doubled as well. Here, I could double the size of the input, and the amount of work I have to do stays the same. Asterisk. Dictionaries are amazing. If you had a situation like this, and you had 1 billion students in your class, now that you know the difference between dictionaries and lists, would you want to do the list of lists or the dictionary for speed? The dictionary, obviously. It's going to be way faster. It doesn't matter how big it is. It's a quick look at one thing, done. Found it. Raise your hand if you're thinking, but how? How does it do that? Like, the linear search makes sense. If you gave me a stack of exams, and you said, let's say they weren't sorted, a stack of exams, and you come to my office and you're like, oh, hey, can I get my exam? I have to start at the top and look at each one, right? I have to find it. And maybe you're the last one at the bottom of the pile. Great. I have to look at all the things. But I'm now suggesting to you that, there's a way that I could magically have something like that, but immediately know where it is. Without having to do that search. That doesn't make any sense. How is that possible? That sounds not possible. Who here kind of feels that way? So, you're normal for thinking that. But these dictionaries, these key value pairs, are quite interesting and magical, and they make total sense. What time we got? 12. Ooh, I suppose I can kind of explain how it goes. Imagine for a second, is this any good? Yeah, perfect. I'm not going to teach you all the nitty-gritty details because there's not enough time, and this really is outside the scope of 161. I'm showing you the high-level idea of how they work, but you'll learn a lot more about them in the future if you keep taking computer science. Here's the idea. Imagine I had this secret long list. It was huge, okay? It was really, really long. Actually, before I draw it, let me make sure I don't actually have this in there. Okay, it looks like I don't. All right, cool. And you give me a key. And you want to say, at this key, James, assign the value 60. If this was a list, you could show up and say, oh, list at location 0, B50. Or be the sublist James 50. Great. But pretend this is a giant list. I realize it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 long, but pretend it's huge. It's hilariously large. And I show up and I say, you know what? I've got a magic function. I have a very magic mathematical function that will take a string. It doesn't have to be a string technically, but let's think about strings. It'll take any string and convert it to a unique integer. Don't worry about what this function is. Just pretend it exists. It's this magic function we will call h. We give this function h some string, and it magically gives me a unique integer. And I will use that unique integer as my index for this hilariously large list. So let's say I put in h of James, and it gives me 4. Oh, okay. So h of James gives me 4. And if I say James B50, I'll go, okay, James, which is really 4, 0, 1, 2, 3, 4, B50. And then if I say h of Sally, oh, that just happens to get mapped to 0. I don't know. Don't ask me where this function came from. It's magic. It gives me 0. Oh, well, Sally, well, at 0, that means 85. I think Sally had 85, maybe he's 95. Who cares? Doesn't matter. Then you come along, h of Greg. That gives me 11. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Whew. Pretend it goes on forever, though. And that gives me, Greg had 95. It's hard to see, but whatever. It's there. This is how it works. So then you show up later, you're like, wait, what's the value associated with James? Oh, well, just pop it back into the function. It tells me 4. Go look at 4. Done. Found it. I didn't have to search anything. But of course, as we see here, there are a couple of drawbacks. Let's say this is my whole list, or pardon me, this is my whole dictionary. 3 value pairs. 3 key value pairs. You might be thinking, but I created this hilariously long list just to store 3 pieces of information. Yeah, I did. But look how fast it was. We wasted space, but look how fast it is. Or you might be asking yourself the question, what the hell is h? How does h magically do this thing? And I'm saying, don't think about it. I'll keep saying, don't think about it right now. But that function is called the hash function. It can turn something into an integer. And then the last problem you might say is, well, okay, so you're telling me don't worry about this, but what happens if I come along and say h of Bob? And h of Bob happens to give me the integer 4. Because I guess this function, there's no way to guarantee really that it's going to map to something unique. I don't know. What if we have like a collision or something? These are all issues that you will talk about a lot in second-year computer science. Right now, we're not going to worry about that. We know that they exist, but we know we can take advantage of these dictionaries for hilariously fast lookups of values from a key. No need for linear search. Just look it up in a dictionary. Great. Okay, we'll end there for the day.